Today we have the pleasure of hosting Professor Kip Thorne from Caltech, the Department of Physics at Caltech. Kip got his PhD in 1965 from Princeton. His advisor was John Wheeler, one of the, founding fathers of relativity, computational relativity, theoretical general relativity. Kip pretty much followed in his footsteps, and over his career made fundamental contributions to gravitational waves from astrophysical sources, and in particular gravitational waves from binary systems of compact objects, neutron stars and black holes, that eventually turned out to be the first discovery from Ligo. I think Kip was one of the first to say that these are black holes that we should expect to see. And with Ligo and not so much neutron stars, early on people had ideas of supernovae. But Kip really led the field in understanding that these are the primary sources, and brought up several generations of theoretical physicists who basically laid the theory that allows us today to understand what we are seeing with Ligo. Kip is here as a Harvey Prize laureate, and as I'm sure most of you know, he is sharing the prize with Ray Weiss that we heard yesterday, and with the late Ron Drever. The three of them received the Harvey Prize for the discovery of black hole binaries and the first detection of gravitational waves in Ligo. So this is part of the part of several talks that you have heard or will hear more this week. It's the last physics talk this week, but I do want to mention that Kip has been very kind to us and is also going to give a popular talk at 6:30 about the movie Interstellar. He actually wrote a book about the science of Interstellar, and that will be followed by the screening of the movie. This will all take place at the Heller Auditorium at the Student Union. So please, Kip, thank you for coming, and you're welcome.
Do you hear me well enough in the back that I can avoid using that mic? Okay, good. And is it possible to cut the lights up front? I think we went through this yesterday. So I'm going to begin by talking a bit historically, and then I will pick up where Ray Weiss left off. I wanted to say a bit about our understanding of gravitational waves in the 1970s. The 1970s, because that was when Ray and I both started working vigorously on issues related to gravitational waves, though we both began to lay foundations for our work in the 1960s. So already in the early 1970s, when Ray and I started working vigorously in this area, we did understand that the difference between electromagnetic and gravitational waves would have major import for the future of this field. Electromagnetic waves in the astronomical context are oscillations of the electromagnetic field propagating through space-time, while gravitational waves, of course, are oscillations in the fabric or shape of space-time itself. So very different kind of physical phenomenon. Electromagnetic waves, again in the astrophysical context, are incoherent superpositions, almost always incoherent superpositions, of emission from individual particles or atoms or molecules, whereas gravitational waves are produced coherently by the bulk motion of matter or energy. In the case of black holes, what we have seen, there's no matter at all involved, but there's a huge amount of energy that moves coherently and emits the waves. Electromagnetic waves are all too easily absorbed and scattered as they travel through interstellar space. Gravitational waves are never significantly absorbed or scattered, even if they're emitted near the Planck era at the beginning of the universe. And so what this means is that first, because of these huge differences, many gravitational wave sources will not be seen electromagnetically, and indeed the gravitational wave sources that we have seen, the 3.87 detections, is that right, Ray? 3.9 detections were not seen electromagnetically, the emerging black holes. Big surprises are likely as we start to look at the universe with this radically different kind of radiation. And there's a real potential for a revolution in our understanding of the universe. And so that was what drove Ray and me and others who began working in this field in the 1970s. At least that's a big piece of what drove us. It was this promise for what we might be able to get out of gravitational wave astronomy. There was a workshop in 1978 that should be Battelle, I misspelled it, workshop on sources of gravitational waves in Seattle, Washington. And this is almost all of the participants in the workshop. As you'll see in a moment, there was at least one person who refused to be in the photograph. But it was a momentous time. I see key people here, the people who pioneered numerical relativity, which I'll talk about, the numerical simulations of sources. Larry Smarr here, Tzvi Piron, Joan Centrella. And then the people who co-founded Ligo. I'm here, Ron Drever is there, and Ray Weiss was the one who chose not to be in the photograph, so I had to paint him in. But this was a very exciting meeting in which we brainstormed both about gravitational wave detection techniques, but in the context of the sources, and we brainstormed in great detail about the sources. The book that came out of the conference called Sources of Gravitational Radiation, edited by Larry Smarr, who was one of the founders of numerical relativity, it has near the end a summary of where we had gotten to here for burst sources or transient sources of gravitational waves as a function of frequency. So 100 hertz here, 1,000 hertz here, 10,000 hertz. So this is the LIGO band. And H, a strain, the dimensionless strain that Ray talked about yesterday, 10 to the minus 20, 10 to the minus 21, 10 to the minus 22. And so the things we were talking about in the LIGO band were supernovae. And we had them up here somewhere around a few 10 to the minus 21 or smaller. We did not yet fully appreciate, and the people who are doing simulations of supernovae on computers did not fully appreciate the consequences of the weak neutral currents, which had just been discovered a few years earlier, and which caused neutrinos to couple to other particles much more strongly than had previously been thought, and as a result would be held in more strongly, and you would provide pressure, and a collapsing star would, in fact, it turned out, more ooze down instead of collapsing down in free fall. And so these predictions were before that was appreciated, and once it was appreciated, that supernova prediction plunged way, way down by several orders of magnitude. And that came sort of a year or two after this workshop. But the other thing that is here particularly important is compact binary destruction, CBD. That is what we now call binary black holes, binary neutron stars, and binaries made of black holes and neutron stars. And the prediction was the maximum signal that we would see here at Earth would be about 10 to the minus 21, and it would be somewhere down below there. And then we were also talking about core quakes in neutron stars that might have a solid core. In fact, the first signal that, so looking at these sources, there came to be a consensus at that meeting that the strongest gravitational waves that we had a reasonable expectation of seeing were 10 to the minus 21 in strain. And so T-shirts were made up, and unfortunately, I have not been able to find any of these T-shirts, but T-shirts were made up that some of us wore at that conference that said 10 to the minus 21 or bust. We will achieve 10 to the minus 21 in this field, or we will fail. And in fact, when the first signal came in, September of 2015, it was right there, 1 times 10 to the minus 21. And so 1978, we knew where we were going. We thought we knew where we were going, and indeed, obviously, partly by luck, we were right on the money as to how strong the first signal was. By the 1980s, it was also clear that in order to underpin LIGO data analysis, in part to find gravitational waves, if they were not so strong that they stuck up above the noise. And then in part, to extract the information carried by the waves, we would need computer simulations of the sources, because the interesting sources would be types of things you could not analyze fully analytically. So you would have to do it by solving Einstein's equations on a computer. This is called numerical relativity. And so numerical relativity is something that had to mature hand in hand with LIGO and in the same time scale reach fruition in order for us to really understand what it was we were seeing. So let me give you a brief history of numerical relativity in parallel with LIGO. The 1960s, when Joe Weber did his experiments and Ray Weiss and others were beginning to think about laser interferometers for gravitational wave detection, Bryce DeWitt, then working at Livermore, California, on the design of thermonuclear weapons, took the codes that he had written for design of thermonuclear weapons, where he had introduced curvilinear coordinates in order to handle that design work, and said, gee, if I can now work in curvilinear coordinates, and I can build any coordinate system I want, I can do numerical relativity. And so he began the first serious efforts at simulating binary black holes. In the 1970s, when Ray wrote his seminal paper that Hood talked about yesterday, and the first prototypes were built at MIT by Ray, at Glasgow, Scotland by Ron Drever and their colleagues, and in Germany by Heinz Billings and his colleagues. In that same time frame, Larry Smarr, who had been trained by Bryce DeWitt and building on the foundations that Bryce had laid, he and his student, Kenneth Epley, had the first successful collision on a computer of head-on collision of two non-spinning black holes. And that was a huge, huge success. And this came, I think, if my memory's right, just before the Battelle Conference was, and it was discussed at that Battelle Conference in 1978. In the 1990s, when the LIGO project, or 1980s, when the LIGO project was founded, Zvi Perron did the first successful simulation of the implosion, the gravitational collapse of a spinning star to produce a spinning black hole, and to compute the embedded gravitational waveforms, the gravitational wave shapes. And here, of course, Larry Smarr and Kenneth Epley also predicted for the head-on collisions of binary black holes, the gravitational wave shapes. And those are the things we needed, the waveforms, the wave shapes, for data analysis. And so we felt pretty good, I think, as a community, that things were rolling along pretty well on the numerical relativity front as well as on the LIGO front. The 1990s, when LIGO facilities were under construction, there was an international collaboration. I have to say that it was Richard Isaacson, the man at NSF, who was really responsible for getting LIGO going in the National Science Foundation, and I think should be regarded as a co-founder of LIGO with Ray and me and Ron. He also was the person who said to the numerical relativists, you're not making fast enough progress, you've got to collaborate. And he forced them to get together and form an alliance to work together. And I was asked to serve as the chairman of the advisory committee to that alliance. So it was all the, and at that point it was perhaps 6 or 7 numerical relativity groups from around the world that all got together, and they would meet twice a year to compare notes, to discuss how things were going, to identify what the problems were, and comment on each other's work. I became rather alarmed by the early 2000s because progress was not as fast as we really needed here. Things were pretty hung up. And they were hung up, it turned out, because of fundamental stuff that was not understood mathematically in Einstein's equations that I can comment on in the question period if you wish. And so in the early 2000s, I left day-to-day involvement in the LIGO project in order to co-found together with Saul Tukolsky at Cornell, co-found a project called SXS to simulate extreme space-times, basically simulate LIGO's gravitational wave sources. And it was our postdoc in the SXS project, Franz Predorius, who's now a full professor at Princeton, as a result of his phenomenal work, he had the big breakthrough in the first successful simulation of two black holes orbiting around each other, spiraling together, colliding, and merging in 2004. By 2015, the SXS project and several other numerical relativity groups were able to simulate the sources that LIGO saw and had codes that were fast enough and accurate enough to meet LIGO's needs. And the person who I think bears more, along with France, deserves more credit than most anybody else for this is Saul Tucholsky, who is the leader of the SXS project, a professor at Cornell. So numerical relativity was ready in time for the first detections. I had a bet with the young people in the SXS, in that 1990s Grand Challenge Alliance, the Binary Black Hole Alliance. I had a bet with them that has been framed now at Caltech, where I said that the experimenters would detect gravitational waves before they could simulate the sources. And I was very, very pleased to lose that bet. So by the time the first gravitational wave was seen, the numerical relativity community had put together 1,000 simulations, that is simulations of 1,000 different binary black hole systems to help underpin the LIGO data analysis. Now, this is not a trivial thing. There are 7 non-trivial parameters for a binary black hole. Here's an example. Here's a black hole that has a mass of 60 solar masses. It's spinning at 91% of the maximum angular momentum of spin, with its spin spin axis pointing in this direction. A 10 solar mass black hole spinning at 30% of the maximum of the spin axis in that direction. Here's the direction to Earth. And here are the 2 waveforms for the 2 different polarizations. These are much more complicated waveforms than we have seen thus far, but this illustrates the fact that we will expect on occasion to see much richer waveforms than what we have thus far seen. But when you have substantial precession, as you do in this kind of a system where this black hole is spinning rather rapidly and the orbit's going to precess, and if you see it roughly edge on, you'll see large modulations. But there are 7 non-trivial parameters for the numerical relativist to deal with. There's the ratio of the masses. And everything just scales with the mass. So the mass is not, from the point of view of the computations, if you double the mass, you have the frequency of the waves, and everything just scales. So the mass ratio and 2 vectorial spins, that's 7 non-trivial parameters. That's a lot to deal with. And 1,000 waveforms just sort of very crudely covers the range that you have of relevance to LIGO. Now, in the data analysis, in those cases where the signal does not stand up so strong that, you can see it by eye, the method of matched filters is the best way to dig deep into the noise to find a signal. So you numerically cross-correlate each of some large number of wave shapes, of waveforms, against the noisy data. And in practice, what is used by the LIGO team is roughly 100,000 different wave shapes. There were only 1,000 simulations done, so how do you get 100,000 wave shapes? Well, obviously you interpolate. So there's a lot of interpolation done. And do it with sufficient accuracy that you don't lose very much in terms of signal to noise. And you also have to have, in 1 month time, about 10 to the 9 start times. That is, at what time does it be, is it right now, or is it a millisecond from now, or 2 milliseconds from now that this piece of the waveform occurs? So that's a total of 10 to the 14, 10 to the 5, 10 to the 9, 10 to the 14 different experiments, if you wish, different cross-correlations that you do in searching for a gravitational wave signal. And you do it on the data from both sides. If the noise is Gaussian, and it's pretty close to Gaussian, then you want to, in order to believe something, you need to have it occur with a probability in each of these experiments less than 10 to the minus 14. And that's way out. When you take account of the fact you're dealing with 2 detectors, it turns out to be out at a signal-noise ratio of 9 or greater. You begin to believe it at 9, to really believe it needs to be 10 or more. And in the first detection, it was at 24. So it was really, really strong compared to the threshold. So the waveforms are computed not just with numerical relativity. Only the piece that you have to do with numerical relativity is done by numerical relativity. And that's the what I would call the geometrodynamical regime, where the space and time are very strongly warped. And the warpage is changing very rapidly. So that's a period of about this length, something like a dozen cycles around the moment of collision of the two black holes. Earlier than that, you can handle things with post-Newtonian approximation. That is an expansion in the orbital velocity divided by the speed of light, or which is assumed to be of the same magnitude as gm over rc squared. R is the separation of the two black holes, just through the virial theorem. And these post-Newtonian methods of expanding to solve Einstein's equations were developed over a period of 40 years, with the major players being roughly 30 theorists, beginning perhaps with Chandrasekhar, Clifford Will, and then the people who had the biggest impact on this, Thibaut Damour and Luc Blanchet. These post-Newtonian expansions up through V over C to the 7th were pretty much in hand by about the year 2000. So there was not a worry there. It was the numerical relativity where the worry was. But this is what's used for the early part of the signal, and then the geometrodynamical regime is done with numerical relativity. That's all put together, and then it's used to tune a set of analytical or quasi-analytical waveforms that basically are fit to these theoretical waveforms. So that's how it's done. And this has been crucial for finding these weaker signals that are long. So the only way it could be found, this signal, is through cross-correlation or match filtering with these theoretical waveforms. That one stood up so strongly above the noise that you could just see it. But that one is also really interesting because everything you saw, every cycle that was seen was in the geometrodynamical regime. So it could only be known what it is through numerical relativity. It couldn't be known through any analytical, quasi-analytical methods. It's this truly, fully numerical relativity regime, that first signal. Now, then to learn the source's details, once you have seen the gravitational waves, you have to compare LIGO's observed waveforms with the theoretical waveforms. And of course, that is what was done to infer for the first signal that you're dealing with a 36 solar mass and 29 solar mass black holes. That's a total of 65. Final black hole is 62. You've turned 3 solar masses into gravitational waves. You did that in a time of a fraction of a second. The total power output is 50 times the luminosity of all the stars in the universe put together during that fraction of a second. Quite impressive. And you also infer that the distance is 1.3 billion light years, and you get similar parameters for the other sources. And for the fourth source, this is an older slide. I haven't added on the signal from last January 4 that was just announced a week or two ago. Now, in order to learn what the black holes were doing during the collision, that is to learn about the geometrodynamics, we make videos of the simulation. So you see which waveform best fits the observed data, and then you go back and you look at that simulation. And in order to understand what the billions of bits of information coming off the simulation are doing, you make a video. So these are the videos, famous videos made for GW150914, the first signal. This is what it would look like to your eyes due to gravitational lensing by the black holes. The dark things are the shadows of the two black holes around each other. If you look carefully, you see there's a lenticular shadow here. This is the gravitational lensing of that shadow by this black hole. And so you see the lensing that's where basically light rays have gone around the black hole several times. And so this is what was played over and over again in the days after the first detection, and made the front pages of many of the newspapers. The people who made this video were 3 graduate students at Cornell, graduate students of Saul Tucholsky's. Will Throw, Andy, God, that's terrible. I think I had their names up here. So Andy Bowen, Francois Hébert, and Will Throw. They got 0 credit for this. It wound up being credited to Ligo in most places, and not even to the SXS collaboration. Then there's another video to understand the geometric dynamics. The black hole is made the black holes are not made from matter, of course, they're made from curved space-time. And so you depict in a sort of an embedding diagram the shape of space as it would be seen if you were looking in from a flat, higher dimensional space in which the equatorial plane, a 2-dimensional surface, is embedded in a flat, higher dimensional space in order for you to be able to see what the shape is, the intrinsic geometry. This is not quite that. It's something close to that, and there's some technical reasons why it's not precisely that, but never mind. The arrows show the dragging of inertial frames, or the dragging of space into motion, heuristically. And the color coding is the slowing of time. And you see here the fantastic storm that created the gravitational waves. It goes into slow motion. The red time is greatly slowed relative to what it is back in the Earth. The black is inside the black hole. At the moment of collision, this is paused. It's like a gigantic storm at sea in the shape of space, and then it vibrates and the gravitational waves go off. I discussed this in a technical seminar day before yesterday on Sunday. And as I described it, there's, that movie shows only a tiny piece of the geometric dynamics. And I'll just very quickly tell you the rest of it is tied up in things called vortex lines that stick out of the black hole that guide the whirling motion of space. This is for a quiescent black hole. If I hang my wife near the black hole or let her fall in, a gyroscope at her feet goes around and around faster than the one at her head because it's closer to the spinning black hole. So she sees a differential precession of gyroscopes at her head and her feet. And if she attaches her head and her feet to the gyroscopes, then she is twisted in a counterclockwise manner. And at the south pole of the black hole, she would be twisted in a clockwise manner. And so there are these vortices of twisting space. We've obviously borrowed the phrase vortex from fluid mechanics that stick out of a spinning black hole. And when 2 black holes orbit around each other, each of them spinning, so each of them with their vortices of twisting space, I show in red the counterclockwise vortices, in blue the clockwise vortices. As they go around each other, collide and merge, those vortices do something interesting. They basically form spiral arms that stick out of the black hole. The counterclockwise vortices are there, the clockwise vortices are here, they all wrap around each other. And as they go traveling out like water from a whirling sprinkler, they generate by their motion tendencies, what we call them, of stretching and squeezing space. And that's what the gravity waves are that are detected by LIGO. They stretch and squeeze a gravity wave detector. And so we now understand in this language, in terms of physical structures that are made from warped space and time, these vortices, these tendencies, we understand how the gravitational waves are generated, and we're beginning to understand geometric dynamics. I'm going to just skip over this. How often do black holes collide? Well, we now have some handle on that. We have 3 firm detections now, and a 4th that is a high probability detection. From that, we conclude that in LIGO's data, roughly 1 every 2 or 3 months, as Ray said yesterday, at LIGO's current sensitivity, which is about 1/3 of design sensitivity. That means that in 2020, when we expect to be at design sensitivity, we'll be seeing 3 times farther into the universe, 3 cubed or 27 times more volume of the universe, and so 27 times higher event rate, so a few per week by about 2020, and I am confident that Ray and his experimental team will reach design sensitivity roughly then. He's less confident. He's always more pessimistic than I am. In a region 1 billion light years on a side, the observations say there's about somewhere, and here you've got the uncertainties between 1 and 20 per year. It's a big uncertainty because you're dealing with small numbers. And in the observable universe, at least a few per hour, and could be much more, but we just don't know what the evolution is because you go back in time into the earlier universe. What else will advanced LIGO see? Well, we expect, by the time we reach design sensitivity, to be seeing periodic gravitational waves from spinning neutron stars, or pulsars, black holes tearing neutron stars apart in black hole neutron star binaries, neutron stars colliding and tearing each other apart in a neutron star binary, leaving something that will almost always be too heavy to continue life as a neutron star and will implode to form a black hole. We will probably not see, because we can't see very far because that reduced supernova signal strength that I mentioned before. But ultimately, somewhere in the life of LIGO, we have a good shot at seeing the cores of supernova explosions. The LIGO team is going after gravitational waves from cosmic strings in the very early universe, defects in the structure of space, basically, that are speculated to have been formed in the very early universe. And this is the big thing. This is the thing that drove us to a great extent. We surely somewhere along the way will start to see some huge surprises that we didn't expect. These things, these sources, by contrast with the binary black holes, are guaranteed to produce other forms of radiation besides gravitational waves. And so we call this multi-messenger astronomy. It involves X-rays and gamma rays, light seen by optical telescopes, radio waves, and neutrinos. So there are agreements, collaborations between the LIGO scientific collaboration and astronomers who work in these various other kinds of radiation. That the LIGO collaboration feeds all the data they can, the relevant data about candidate signals, the moment a candidate signal is identified, to the collaborators, and they go and look as quickly as they can to see if they can see any counterpart. And we expect to see a lot of counterparts once we're seeing things beyond binary black holes. There's a big problem, though. We really need to tell the electromagnetic astronomers where they should look. And as Ray indicated, the error boxes on the sky for the current LIGO detections, there's the first one, which is really strong. That's that error box. It was overhead at the Antarctic Peninsula, roughly. And the second and the third ones, there are two different regions. We don't know whether it was up here or whether it was down there. These are huge error boxes, and that's not a very nice thing to be giving to an electromagnetic astronomer, saying, okay, go look somewhere there. And so the key thing is to be able to get smaller error boxes, and because the directionality comes primarily from the delay in the time of arrival of a signal at different locations on the Earth, the name of the game is to get other detectors up and running, so you have more time delays than just between Hanford, Washington, and Livingston, Louisiana. So the Virgo detector, as Ray indicated, is likely to go into operation with and run in a gravity wave search with LIGO this summer. As Ray explained, there are plans to put a LIGO detector in India, and the Japanese collaborators have a detector called Kagra that's being installed in the Kamioka mine in Japan. With LIGO and Virgo alone, here are the error boxes that you would see, and they're really still pretty awful. But as soon as you bring in LIGO India, they get a lot better. And then Kagra improves things in the east-west direction, but they're already pretty darn good in the east-west direction. So the key thing is LIGO India to get down to reasonable-sized error boxes, more or less the size of the moon or the sun. Beyond advanced LIGO, in the early 2020s, there are plans for something that's called Advanced LIGO Plus, or A+. And LIGO India should be beginning to operate at that time. And the design for this would enable it to see 1.6 times farther black hole collisions than at the level of a few per day. Late 2020s, there are tentative plans. There's a design, and there are discussions for something called Voyager, or the third generation of LIGO, which would see 2 times farther than LIGO A+, black hole collisions roughly 1 an hour, and of course lots of other stuff we do expect. And then the 2030s, a 4th generation instrument, the Cosmic Explorer in the US, the Einstein telescope in Europe, 40-kilometer arms, seeing 5 times farther than Voyager, should be capable of seeing every black hole in the universe with masses less than a few hundred solar masses. Every black hole binary merger in the universe. So this is, if all goes well, this is how we expect things to evolve over the next 15 to 20 years. The 2 biggest issues in moving forward along this path are noise in the mirror coatings and so-called quantum noise, which I will just talk very briefly about. I think Ray said something about this in the question and answer period yesterday. The mirror coatings are alternate layers of dielectric with different indices of refraction. So you have a high refractive index, then a low refractive index, and a total thickness of the wavelength of the light divided by 2 for this pair of high and low refractive indices, and lambda over 4 for the thickness of each one. And by putting on layer after layer after layer like that, you build up the very high reflectivities at the level of 10 to the 1 minus 10 to the minus 5, that is losses of 10 to the minus 5 that is achieved in the LIGO mirrors. But the problem is that mechanically, this stuff is very noisy. There's a lot of friction in there. If it's set vibrating at all, there's a huge amount of friction in these dielectric layers. And so there's a big effort underway to find new materials for these dielectric layers that will have much lower friction and correspondingly, according to the fluctuation dissipation theorem, much lower fluctuational forces and much lower thermal noise then. The quantum noise is an issue that Vladimir Brzezinski, our Russian colleague that Ray, I think, talked a little bit about yesterday, Vladimir Brzezinski told us about in 1968. That's 50 years ago. And he said, no matter how you build a gravity wave detector, if you're going to have success, you're going to have to face up to a macroscopic object behaving quantum mechanically. And the way that plays out is Carlton Case was the first person to show really clearly in LIGO, is that if you've got the thermal noise under control, your light beam is just measuring the center of mass motions of these mirrors. So you're looking at the separation between the centers of masses of these mirrors. So these mirrors are behaving like quantum mechanical particles that weigh 40 kilograms. And the measurements that are being made at design sensitivity are at the level of the half width of the Schrodinger wave function of the center of mass degree of freedom of these mirrors. And so you're dealing with mirrors that are behaving as quantum mechanical particles that weigh 40 kilograms. So for the first time, humans will see human-sized objects behaving quantum mechanically when advanced LIGO reaches design sensitivity. And for the 3rd generation, for Voyager and beyond, you're well below that level. So you're having to dig down into the quantum noise that's associated with the Heisenberg uncertainty principle. And so the name of the game is what Brzezinski called quantum non-demolition technology to deal with this. How do you get a highly classical gravitational wave through particles that weigh 40 kilograms whose motions are being used to monitor the gravitational wave? How do you get it through unscathed? How do you get a classical gravitational wave through these quantum particles without demolishing the signal? And another way to say it is, how do you make the output signal insensitive to the quantum state of the mirrors? And I talked about how you do that on Sunday, and I'm not going to talk about it anymore here unless you ask me a question at the end. So I want to now turn, for the next little bit, to other gravitational windows onto the universe. So the LIGO gravitational wave detector operates going after gravitational waves that have periods of milliseconds. There is 2 detectors in the future. I'm going to talk about each of these in just a little bit of detail. LISA and the Big Bang Observer, that go after gravitational waves with periods in the minutes to hours region. They involve spacecraft that track each other with laser beams. Then there is now in operation searches for gravitational waves using things called pulsar timing arrays. So this is radio astronomy technology, going after gravitational waves with periods of years to decades. And finally, there is the polarization of the cosmic microwave background, so-called B-mode polarization, that is expected to carry a gravitational wave signal from gravitational waves that came from the birth of the universe, from the era of inflation in the earliest moments of the universe. And that corresponds to gravitational wave periods of the period of those waves today would be hundreds of millions to billions of years. So obviously you don't sit around as a graduate student and wait for one period. You look for the pattern on the sky instead. But these 4 bands we expect to all be fully opened up by sometime in the early 2030s. So the next 15, 20 years, within the next 2 decades, it will be as though you had opened up optical astronomy with telescopes, radio astronomy, infrared astronomy, and X-ray astronomy all over a period of 15 to 20 years. And so that is another place that this field is going. Let me say a few words then about LISA. LISA is a project with 3 spacecraft that track each other with laser beams with approximately 5 million kilometers between the spacecraft. You don't have light going out and bouncing back and forth between mirrors like you do in Ligo. There's no way to do that because you have something like a 30-centimeter telescope that's focusing that light. And over 5 million kilometers, the light that goes through that telescope, due to diffraction, is going to diverge, and the beam is going to be kilometers across with a little 30-centimeter telescope there to capture a tiny fraction of the photons. And so there's no way to bounce the light back and forth. There's no way to lock the arms together like you do in Ligo. So they're separated by an integral number of half wavelengths of light. Instead, the spacecraft move with each other slowly as you can organize them to do without having to apply thrusters onto them very much. And you just count fringes as the fringes go by. And so it's a very different way of doing the optics, but it's a way that is capable of achieving the sensitivities that you are required to do some very exciting science. At almost the same time as LIGO made its discovery, the European Space Agency launched into orbit around the Earth and a LISA Pathfinder mission to test the most dangerous of the technologies for LISA. And this is a little movie made by the European Space Agency about that Pathfinder mission. This was made before the mission flew, but it explains what's going on in this mission.
LISA Pathfinder will operate 1.5 million kilometers from Earth towards the Sun, orbiting a stable point called the First Sun-Earth Lagrange Point, or L1. There, it will test technology for future space-based observatories to detect gravitational waves. It will do so by monitoring the motion of 2 cubes that will free fall in space, separated by 38 centimeters. Between them, a laser interferometer will measure the relative separation of the 2 cubes to unprecedented accuracy, as external and internal forces disturb the spacecraft around them. Housed in 2 vacuum enclosures, the free-falling cubes sit at the core of the science module. On top, a solar array provides power to the instrumentation and acts as a thermal shield. Several sets of microneutron thrusters, located on the outer panels, will continually apply minuscule amounts of force to move the spacecraft and keep it centered on one of the cubes. This experiment will demonstrate that it is possible to put two test masses in a nearly perfect freefall motion. This is an essential underlying condition to detect gravitational waves from space.
So the biggest worry, I think, that the experts had about the LISA technology is those little cubes, and whether or not you can really make them have no forces on them except gravity at the required level. There was a similar problem in what was called Gravity Probe B, where instead of cubes, it was spinning spheres, gyroscopes. This was to measure the dragging of inertial frames by the spin of the Earth. And Gravity Probe B ran into major problems that caused it, although it did succeed in measuring the dragging of inertial frames, it was at a level of precision that was several times lower than it should have been. And after having the problems with Gravity Probe B, the funding agencies, NASA and ESA, got really scared with regard to this kind of very high precision stuff in space. And so it was particularly crucial to have the LISA Pathfinder mission fly and see whether or not the LISA team has all the issues under control so that these little masses would move freely under the influence only of gravity to the required precision. So here is the results from the first paper from that experiment that was published. The paper, I think, was published just a matter of a few weeks ago, if my memory is right. So the LISA Pathfinder requirements, here this is the spectral density of the acceleration of the test masses relative to an inertial reference frame, or basically relative to each other. And this is the frequency. And the LISA frequency band is basically 10 to the minus 1 hertz up to 10 to the minus 4 hertz. And so you wanted very low acceleration noise there. The LISA Pathfinder requirement was here. LISA's requirement is there. And here's the experimental noise. And so they did much better than the Pathfinder requirement and very close to the LISA requirement itself. Now, I think Ray will tell you that that was in part because they pulled back on what their requirement was. I think this is where they really hoped to be, and that is where they really did come in. But it's a huge triumph. It's really a huge triumph when you look at this. And that coming hand in hand within a matter of weeks, when the first results were announced from the Pathfinder mission, of LIGO's first detection, has driven LISA suddenly from being a mission that people were scared of in the funding agencies at ESA to something that is starting to become very high priority. And so we're very hopeful that LISA will move forward. In the end, as a joint European-American mission. It was originally a European-American joint ESA-NASA mission, and NASA pulled out because of cost overruns on the James Webb Space Telescope. And NASA is, we hope, we're ready to jump back in and join in and provide additional help to the Europeans that would enable this mission to be pulled off successfully. LISA's science is very exciting. Binary black holes with masses from 10 to the 4 to 10 to the 7 solar masses. Signal-to-noise ratios as high as 10,000 compared to LIGO's thus far. The largest was 24. And LIGO will be up in the several hundred in the next decade. But still 10,000. Just imagine what you learn about geometric dynamics with a signal-noise ratio of 10,000. If you want to map the space-time geometry of a black hole, shown here by an embedding diagram for the shape of space, color coding of the slowing of time, arrows showing the dragging of inertial frames, this is a full depiction of the space-time geometry in the equatorial plane of a black hole. Take a small black hole, let it orbit around, spiral into a big black hole, it emits gravitational waves, collect data over a period of a year, analyze the data, and the observed gravitational waveform, it turns out, carries a full map of the space-time geometry of the big hole that's being explored by the little hole as the little hole orbits around. And you can appreciate why it contains a full map by looking at the orbit. The orbit does not resemble the orbit of any planet you've ever seen because it's being whipped around by the dragging of inertial frames, by these vortices of twisting space, as well as by the gravity of the big black hole, and as well as by the space-time curvature, the tendencies, the stretching and squeezing. And so it really does explore the whole region around the big black hole, and the waveforms really do. It has been shown by Fintan Ryan, a graduate student of mine who then went off to Wall Street after doing a superb PhD thesis. He proved that the map is all in there. And what if the central body is not a black hole, for example, a naked singularity? Then the orbits are very different. It could be a chaotic orbit, for example, in the case of this particular example. And the waveform, the maps that you get out are going to be radically different. So this is a way to search for unexpected kinds of massive objects that have small black holes going around them. I don't expect to see anything except big black holes. But boy, if we did see something else, it would be really fantastic. Another thing that LISA can be expected to see is the birth of the electromagnetic force, if we're lucky. The key issue is that when the universe is 10 to the minus 12 seconds old, that's when, as the universe cooled, the electroweak phase transition is predicted to have occurred. So the electromagnetic force and the weak force came apart, gaining their own identities. If this occurred in a first-order phase transition, and we don't know whether it's first order or not, then you form, according to the theory, bubbles of the new forces. So the electromagnetic force exists inside this bubble, inside that bubble, does not exist in the bulk outside the bubbles. These bubbles expand at the speed of light, collide, emit gravitational waves, and then as the universe expands from 10 to the minus 12 seconds age to the current universe, those gravitational waves are shifted into LISA's domain, frequency domain. And so they're in just the right frequency domain to be seen by LISA. LIGO could see similar phase transitions at age 10 to the minus 22 seconds, but we have no idea what physics was going on at age 10 to the minus 22 seconds. Pulsar timing arrays are another technique for searching for gravitational waves that I mentioned, looking for gravitational waves with periods basically of order a year or a few years. In this, you sit with radio telescopes on the surface of the Earth, and they look at pulsars and time the radio wave pulses coming from pulsars. When a gravitational wave sweeps over the Earth, roughly speaking, it speeds up and slows down our clocks on Earth. So the rate of pulses from these pulsars all synchronously slow down and speed up. Now that's a slight sheet. Really what it's doing is it's producing a varying index of refraction, in effect, a varying index of refraction. But again, it's more or less like speeding up and slowing down time. And so you see this by timing an array of pulsars. And there are three collaborations that have been doing this: the European Pulsar Timing Array Collaboration, Nanograv in North America, and the Australian collaboration that uses the Parkes antenna. They have all come together to form the International Pulsar Timing Array. And they are at a level of sensitivity where they could be seeing now gravitational waves from massive black hole binaries, masses of 10 to the 8 masses on up to whatever the highest masses are for binary black holes in galactic nuclei. Nothing has been seen yet, but they are in the right ballpark to see something, pushing hard to improve their sensitivities. Finally, the fourth approach to gravitational wave detection that I think is probably familiar to many of you is the cosmic microwave background polarization. The story is that whatever came off of the Big Bang, and conventional theory says that's vacuum fluctuations of the gravitational field, will have been parametrically amplified in the inflationary era of the universe, assuming inflation really did occur, to produce a fairly rich spectrum of gravitational waves, which then interacted with the primordial plasma. When the primordial plasma was recombining and becoming neutral at age 380,000 years, that's when the last scattering of photons by the primordial plasma occurred. And that interaction is predicted to have put a polarization pattern called a B-mode pattern onto the cosmic microwave background, onto the microwave photons that we see today on the sky. And so the search for that is underway. The B-mode pattern has been seen, as is well known by the BICEP collaboration. But what they saw could well all be due to this kind of a pattern being produced by emission from dust. And so the big effort now is to map the dust and separate out what is really coming from this process of primordial gravitational waves and what is really coming from dust. And I think that ought to be sorted out within a matter of a few years, and this will be very exciting. It'll be the first observation of gravitational waves from the, basically, what came off the Big Bang convolved with inflation. And finally, a LISA-like array of satellites with shorter arms and with the arms actually locked. Here is a triangular array. There's a triangular array. That's the sun. This is the orbit of the Earth around the sun. And then a Star of David array. This array is designed to be able to go after, and this is something that could fly in the middle of the present century, well after LISA flies. Go after the last year of in-spiral of every neutron star binary, neutron star black hole, and black hole binary at redshifts less than 8. Get sub-arc second positions on all these binaries. Measure luminosity distances to less than 1%. Measure the Hubble constant to a part in 1,000, and the parameters associated with the acceleration of the universe to remarkable precision. And see stochastic background for the Big Bang at a level where it is expected to see stuff. So that by the middle of this century, 2050 time frame perhaps, if we're lucky, we could have measurements, studies of gravitational waves from the Big Bang in 2 widely separated frequency bands. The cosmic microwave background polarization at periods of hundreds of millions to billions of years, and then the Big Bang observer at periods of something like 10 seconds or to a minute. That will really be an exciting time. And so in conclusion, gravitational waves are going to be a major tool for astronomy, not just for the next few years or the next few decades, but into the next century and beyond. Thanks.
Yes, Asa, please.
What kind of signal do you expect to see from the Big Bang?
So conventional wisdom says that the Big Bang had nothing came off of it except vacuum fluctuations. It was highly isotropic. Of course, there's those contrarian theorists who would like to argue otherwise. If that's the case, then there is a predicted spectrum that you would see that is basically over most of the frequency band. It's basically an almost flat spectrum, but I am kind of skeptical that we really understand what came off the Big Bang. And I'd be a little surprised myself if it was vacuum fluctuations. And that's why I find this so exciting, is that if you can go in and actually measure, you then have to deconvolve whatever you see with the amplification due to inflation. But if you can get measurements in these 2 different, very, very different frequency bands, that will tell you an awful lot and really strongly constrain both the theory of inflation and the theory of the Big Bang itself.
Can you comment regarding the dispersion of gravitational waves?
Yeah, so of course dispersion is caused for electromagnetic waves when the electromagnetic wave goes through a gas made of oscillators, and it excites the oscillations. I mean, these are atoms generally. It excites oscillations that re-radiate in the forward direction. And so the strongest kind of a dispersive medium I can think of for gravitational waves would be, let's make a universe, a hypothetical universe that has nothing in the universe except neutron stars. These are pretty good gravitational wave emitters because they're so compact. It has enough of the neutron stars that the universe is closed spatially. And somehow you artificially hold it so it doesn't expand really fast or collapse really fast. This is just a thought experiment. You can then compute the amount of dispersion you get when the gravitational wave goes around the universe once and back to where it started. And it's about 1 wavelength delay. That is, the dispersion slows the thing down by 1 wavelength of the, and this assumes that the gravitational waves are near the resonant frequencies of the vibration of the neutron stars. So that just gives you some heuristic measure of how very, very weak the interaction is with matter. Another measure is the prediction that the amount of absorption or scattering in the very, very early universe around the Planck era is negligible, a prediction made by Zeldovich back in the 1970s. Another measure is that the first gravitational wave signal that came entered the Earth around the Antarctic Peninsula, and it arrived at the Ligo sites coming up through the Earth, and it wasn't affected. Of course, that's not as strong, but you can go through a number of things of this sort. And the bottom line is that you just don't expect interaction with matter to do much of significance. That's not entirely true. If you have a sufficiently short wavelength gravitational wave that you're in a geometric optics limit, then it's guided by rays that are null geodesics in space-time, just like light. It's the same rays as with light because it's propagating also at the same speed. So you do have all of the gravitational light deflection gravitational deflection of gravitational rays that's identical to gravitational deflection of light rays. So all those kinds of geometrical optics phenomena, those do occur, but those are gravitational phenomena. They're interaction with the gravitational fields of matter, not directly interacting with matter.
What's back there?
If the universe is full of gravitational waves, like you said, so is there interference between gravitational waves?
So gravitational waves, like any other kind of a wave, if you superpose 2 waves, they will add linearly. They'll interfere in the usual manner. But they just pass through each other unscathed. There's no significant nonlinear interaction once you get into the wave zone. So it's just linear superposition. It's often asked then, how do you separate out if you have several gravitational wave signals coming in simultaneously, how do you separate them out? And the answer is the same way as you separate out the signals from 100 different television channels. You tune your instrument to go after them separately if you know what the waveforms are like.
Were you surprised when you first saw all this black hole merging, popping out all this instead of neutron stars? So why is that we don't see neutron stars? Is it because the signal is too weak, or because
the signals are weaker? So I was not surprised. Yeah. Okay. So was I surprised that what we saw first were these massive black hole binaries instead of neutron star binaries? And why did we see the black hole binaries instead of neutron star binaries? So I had expected, going back to about 1980, that this is what we would see. And that's why I pushed the numerical relativity people so hard to do these simulations. And the reason is, it was simple. It's not quantitative at all. Well, the reason is this, that the distance to which you can see a compact binary is approximately proportional to the mass of the binary. Assuming that the mass ratio in the 2 binaries is the same, then it just scales with the total mass. And neutron star binaries, total mass of the binary is about 3 solar masses. We were expecting that the heaviest black hole binaries you would see might be something like 15 solar masses for each black hole, so 30 solar masses. So I was expecting you could see 10 times farther for black hole binaries than for neutron star binaries. So you would see a volume 1,000 times bigger, and it just seemed to me likely, just not based on any real knowledge, just sort of some sense of how the universe works, that factor of 1,000 would be much bigger than the lower absolute event rate for black hole binary mergers than neutron stars. And that's the way it turned out to be. Except that it wasn't, the total masses of the black hole binaries weren't 30 solar masses, they were closer to 60 solar masses. And so that factor, instead of being 1,000, was more like 10,000. And that factor of 10,000 just clearly it has very much, it has significantly exceeded the, more than compensated for the lower absolutely event rate for the black hole binaries compared to neutron star binaries. We know a lot more about event rates for neutron star binaries than for black hole binaries from other observations. We know we have a few neutron star binaries in our own galaxy that will merge in less than the age of the galaxy. And from that, you infer that LIGO, with pretty high confidence, advanced LIGO should see a few. Just how many depends on who does the calculation. But most of the experts say we should see a few at design sensitivity in 2020 or whenever it's reached.
Yes, please.
You mentioned the geometrical regime of short wavelengths and the analog of gravitational lensing, gravity waves. Well, in that regime, you also get caustics.
Yes.
And on caustics, you get intensification wavelengths of -1/3 typically. Would that make any such detection feasible, waiting for caustics to cross you?
So if you had a sufficiently short wavelength gravitational wave, and it passed through the sun, it will be lensed, gravitationally lensed by the sun, but most of the lensing comes from the inner, something like 1/3 of the sun, where the mass is, the sun's pretty centrally condensed. So it turns out there's a focus. It's not a good focus, it's a caustic. You get a caustic out near the orbit of Uranus, the planet Uranus. So you could go put a gravity wave detector there and see significant amplification. But you have to then look at how short a wavelength do you need, which means how high a frequency do you need. And it turns out that you need something above about 10,000 hertz. And we don't know any sources that radiate up there. The sources that we expect from neutron stars and black holes, which are the strong sources, the radiation is concentrated down below 10,000 hertz. And so unfortunately, as nice as that idea is, and it's an idea that was pushed by, I forget who was it that did a PhD thesis on this from Stanford, then went to JPL. I've forgotten, but there was a Stanford PhD thesis, and then they worked further on this at JPL. It just turns out that when you look carefully at the issue of diffraction, you just get too much diffraction unless the wavelength, unless the gravity wave frequency is higher than 10,000 hertz. So I don't know of any way in the solar system to get significant lensing, to get a significant amplification for realistic gravitational wave sources.
The tidal torques become very large during the merger, so that should enhance the Hawking radiation. Is there any significant effect?
Well, of course, the Hawking radiation for these big black holes is extremely small because the wavelength that's radiated is comparable to the size of the black hole. And that's a very, very low temperature. And so, although there may be some enhancement, it's still, I think, I've not done any numbers, but I would be pretty confident it's too weak to be of any to be seen or to be of any practical interest.
So just we stop here. Let's thank Kip.